MSM3, we are on the last unit lesson for Unit 3, Lesson 8 we are on, and it's about inequalities. We need to investigate the properties of inequalities, so let's start with the one below. 12 is greater than 4. That's a true statement. 12 is greater than 4. What we want to do is look at what happens when we do things to that. So what happens if we add 5 to both sides? Well, I would have that 17 is greater than 9. Question, is that still a true statement? If I add 5 to both sides, is 17 greater than 9? And we would say yes. Subtract 10 from both sides. So 12 take away 10 would be 2. Is that still greater than 4 take away 10, which would be negative 6? And we would say yes, that is still a true statement. What if we add negative 8 to both sides? So 12 plus negative 8 is 4. And 4 plus negative 8 is negative 4. Is it still greater? Is 4 still greater than negative 4? We would say yes. Subtract negative 2 from both sides. So if I have 12 take away negative 2, that's the same as 12 plus 2. That would give me 14. And if I had 4 take away negative 2, that would be the same as 4 plus 2. And that would be 6. So is 14 greater than 6? And we would say yes, that's still a true statement. What if we multiply both sides by 5? Is 60 greater than 20? Yes, that's great. And what if we divide both sides by 2? 12 divided by 2 is 6. 4 divided by 2 is 2. Is 6 greater than 2? And we would say yes. So this is great. There's lots of things that we can do to both sides of an inequality where the left side is still, in this case, greater than the right side, meaning the statement still stays a true statement. So the next one says, what if we multiply both sides by negative 6? So 12 times negative 6 is negative 72. And 4 times negative 6 is negative 24. Is negative 72 greater than negative 24? And we would have to say, no, it's not, because negative 72 is much further in debt than negative 24. Or if we were digging a hole, negative 72 would be much lower than negative 24, right? 72 feet below the surface would be deeper than 24 feet below the surface. If we divide both sides by negative 4, so 12 divided by negative 4 would be negative 3. Is that greater than 4 divided by negative 4, which is negative 1? And we would also have to say no to this. So what we've learned is that we can add things to both sides, we can subtract things from both sides, and we can multiply both sides by 5 or divide both sides by 2. Those all stay a true statement. But when we start to multiply by a negative or divide by a negative, the inequality is no longer true. Well, what that means is that we have to flip the inequality whenever you multiply or divide by a negative number. So in order for it to still be true, you would have to say, no, 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 negative 72 is less than negative 24. Or no, negative 3 is actually less than negative 1. So by flipping the inequality, anytime we multiply or divide both sides by a negative, that makes it a true statement again. So let's look at some actual inequalities that we can solve that use this. So this one says negative 12 is less than 3m. So we treat solving inequalities just like we treat equations. So I would look at this and say, where is the variable? It's on the right. What operation is on the right? 3m is multiplication. So I'm going to do the inverse of multiplying by 3, which would be dividing by 3 on both sides. So negative 12 divided by 3 is negative 4, less than the 3's brings me with an m. So first of all, I divided both sides by 3, which is a positive number. I happened to have a negative number here and get a negative answer, but the thing that we just mentioned on the front was, did you divide by a negative on both sides? Did you multiply by a negative on both sides? And I didn't. The thing that is in my handwriting that's on both sides is a positive. The other catch is that we always talk about putting the variable on the left. Still true for inequalities. So if I bring the m over to the left, notice how the big open part of the symbol is closest to the m? When I switch the order, the big open part still needs to stay closest to the m. Any value where m is greater than negative 4 will make the original inequality true. We're going to do a few of these. Negative 2x is less than 8. Sorry, that says negative 2x is less than 6. So I'm going to look at the side of the variable, and I see multiplication. So I'm going to divide the left by negative 2, and I'm going to divide the right by negative 2. So this time, notice the thing that I wrote down was dividing both sides by a negative. Divide D-I-V-I-D-E, both sides by -2. So because I did that, when I write my answer, -2 divided by -2 cancels, and I have an x, I need to flip that less than to a greater than, and then 6 divided by -2 is -3. So the big thing here, because I divided both sides by a negative, I had to flip the inequality in order for it to be still a true statement. I have another one here that is also an inequality. This one's going to be a two-step. I'm going to solve it just like I would an equation. I'll add 3 to both sides. Okay, that works no problem, adding something to both sides. -3 plus 3, greater than or equal than symbol. -2 plus 3 is 1. Here's the part that comes up that really matters. This says x divided by -2. The inverse is multiplying the left by -2 and multiplying the right by -2. So it cancels on the left, but what I just did was I multiplied both sides by -2. So because I multiplied both sides by a negative, when I write down the next step, x is, and I'm going to have to write less than or equal to 1 times -2 is -2. That's because I had to flip the sign in order to keep the statement true. And I had to flip the sign because I multiplied both sides by a negative. All right. Next one here, this looks a little bit more like we're sort of used to, looks a little more like standard two-step equation. Variables on the left, I'm going to subtract a 17 from both sides. -3x greater than symbol, -4 minus 17 is -21. I subtracted from both sides, that doesn't change anything. But I've got -3x, that's multiplication. So I'm going to divide the left by -3 and divide the right by -3. So divide both sides by -3. When I divide both sides by a negative, x is now, flip that inequality, less than, negative divided by a negative is +7. All right, next one, you're gonna like this one a little bit more because this one, standard two-step equation, I don't see any negatives over here on the left. That's a good sign. Subtract 77 from both sides. 5b is greater than or equal to -170. I was combining two things that are negative, get a lot of negatives. Divide the left by 5, divide the right by 5. B is greater than or equal to -34. No flipping because I did not multiply or divide both sides by a negative. Last but not least, we'll put into play what we did in the previous lesson. We're going to distribute, first of all, -3 times 5x, -3 times -4. And now I have a two-step equation that looks pretty standard. I look on the left side, the number being added or subtracted is the +12. I'm going to subtract 12 on both sides. -15x less than or equal to 45. I've got multiplication on the left, so I'm going to use the inverse. I'm going to divide by -15, divide by -15. Because I divide both sides by -15, I'm going to have to say x is, flip my sign, greater than or equal to -3. All right, so we've done a few examples of that. The only time we flip that sign is if we have to multiply or divide both of the sides in our own handwriting by a negative. Graphing inequalities. When we graph inequalities, we're graphing something that has a less than or equal than sign. Sorry, less than or greater than. So this one, greater than. This one is less than. Anytime you do that, you will have what's called an open circle because you do not include the number. If you go to Disney World and a child is less than 3 years old, they get in for free. So the 3-year-old has to pay, but the less than 3-year-olds get in for free. So we do not include the 3-year-olds because we would say the age to get in for free is anyone who is less than 3. So again, that's a less than sign. We do not include the 3-year-olds in the get in free. When graphing, this one says greater than or equal to. This one says less than or equal to. And we use a closed circle on this one because you do include the value. So sometimes you go to that amusement park and you will see, or maybe it's a carnival, and you'll see a ride that says you must be this tall to ride the ride. So maybe your height has to be greater than or equal to 54 inches. So the person who's 54 inches tall gets to ride. They do get to ride because of that little equal sign. So they are included, and we would use what's called a closed circle. So an open circle is just that. It's a circle where we don't color it in. And a closed circle is one where we do color it in because the number is included. So just a couple examples down here at the bottom. Graph the inequalities below on a number line. X is less than 7. I'm going to put the 7 right in the middle. I'm also going to make sure there's a total of at least 5 numbers on my number line. The less than symbol means it's going to be an open circle. And I'm going to draw on my number line an arrow pointing towards all the values that are less than 7. So everything that goes that way, 6, 5, 4, 3, 2, 1, and all the negatives and 0, they are numbers that are less than 7. They would make this a true statement. This one is an interval. -1, 0, 1, 2, 3. I should have started at a different number, but I didn't. I'll be okay. You want to make sure there's always some numbers on either side. You never want your circles all the way to the left or all the way to the right. So 8 is going to have an open circle because it doesn't have the little equal to part, just like the one above. But the 3 is going to have a closed circle because it does have the equal to part. So a child who is 3 years old but has not yet reached 8 might pay, say, a child's price on the kids menu for something. So you've got to be under 8, but you can be as young as 3. So 3-year-olds are included, but anyone who is under 8. Write an inequality that describes each situation below, then graph it on a number line. Haley's grade is at least 80%. So 80% is going to go right here in the middle. So maybe here would be 85%, here would be 90%, and then lower than that would be the 70s. At least 80%. So at the very least, she could have an 80. But if it's at least, if 80 is the least it could possibly be, then we would point our arrow towards the bigger numbers. All of this could be represented, let's say, by the letter G for her grade. So her grade has to be greater than or equal to, right? It could be an 80 or it could be greater than an 80. So greater than or equal to 80. We also need to define our variable. G is going to stand for Haley's grade. We might even put that it's in percent form. Last but not least, Mrs. Fraser owns at least 19, but not more than 27 Disney shirts. Now, this is good for an example, but it's not the truth. I definitely own more than that. So let's say down here is going to be 15, 20, 25, 30, 35. At least 5 numbers. 19 isn't on here, but I can put a circle at 19. 27 isn't on here, but I can put a circle at 27. She owns at least 19. So 19 is the lowest possible, which means 19 could be included, but not more than 27. So 27 also could be included, just not more than 27. Now in here would be all of her number of shirts. So maybe I use S. So what is the rest of this going to look like? Well, the two symbols are always going to be the same and they're always going to agree. They will always be saying it's between 19 and 27. And then you need to say 19 is included by putting the equal to and 27 is included by putting the equal to. Then you would say S equals number of Mrs. Fraser's Disney shirts. And this is very much out of date at this point, but I can still draw a graph, I can still write my inequality, and I can still define my variable.